Hi, everybody. This is Mr. Folly. Oops. And welcome to, I hope, the last of Big Idea 5's podcast. So here we go. 5.4, elementary reactions and reaction mechanisms. Okay. Elementary is supposed to mean easy, but we'll see. Elementary reactions and reaction mechanisms. Elementary steps are the steps that make up an overall reaction. So they make up the steps, so they should be simple. Okay. A slow elementary step determines the orders and the rate law. So this is the part that helps you determine the order and the rate law. Okay. Intermediates pull down the reactants above and add them to the rate law. Elementary reactions have one step, and that means the entire reaction happens all at once. Okay. There's elementary steps and elementary reactions. This is the only time, the coefficients must be the exponents of the rate law if elementary step is slow. So you need it to be slow in order for the coefficients to be the exponents. Higher order reactions are more difficult to execute, so they are more rare. Third order happens but shouldn't be expected. Think a 5'9" guy dunking a basketball, and let me show you what that would look like. I know Spud Webb is 5'7", but you get the idea. I don't think you get the, oh, look at that. Oh, Spud Webb, get out of here. Boom, here we go. Go up. Whoa. Okay, so now if you think that that's the norm, sadly, you're wrong. Okay, so it can happen, but you shouldn't expect it to happen. Mechanisms must match the rate law and the stoic, and what that means by the stoic is canceling correctly. So let's take a look at what that would be like. So H2O2 plus 3I negative plus 2H positive yields I3 negative plus H2O. Okay, so water's not going to be in our rate law if we were doing rate laws, okay, because water's a liquid. Now, it could happen if it's a gas, then it could be in there, but the other ions and things aren't going to be in there. But let's take a look. Okay, so two mechanisms are proposed. Mechanism one with the first step or the rate determining step. So what that means is, if I look at this one, this means my rate law equals K, and I'm looking at my reactants, H2O2 to the first, I negative to the first. And it has to be that, okay? So that's what the rate law is going to be. And then I'm going to have to add all of these things together. So I know OI isn't in there, so OIs are going to cancel. See how there's no OI over here, right? There's two H positives, so let's see what else cancels here. Hoi isn't in the final answer, so I'll get rid of my hois. Let's see here. I2 is not a product, so let's get rid of my I2s. Notice that's got to be the same on both sides. And then let's see what we have left. On the left-hand side, I have one H2O. I'm sorry, H2O2 plus 1, 2, 3 I negatives. Uh-oh. I missed canceling some H. Oh, nope. They're not canceled. They're in there. Plus 2 H positives. See how those are here? Boom, boom. Yields 2 waters. Plus I3 negative. So that matches up here. So that looks good. All right. Two mechanisms are proposed. There's one of them. Mechanism one with the second step being the rate determining step. So if that's the case, let me change my color here. We know that it cancels out if it's the second step. So do you see I have Hoi here? Hoi means I have to pull down this guy, okay? So rate is going to be H2O2. Oops, I forgot K. K, H2O2, I negative squared because I have 2 right here, and H positive squared, 2 H positives. Notice how the Hois cancel out, okay? So those won't be there. Now this one makes me go, no, because the overall order is 5, and that's just too much, right? Oh my goodness, did I look at the wrong one? I did. On my red one, I just looked at the wrong one. So I'm going to save this for just a second. That is my order for this guy right here, mechanism 2 with the second step rate determining. So I got to do this one with the second step rate determining. So I'll make this go, let's go green. So we're going to do mechanism 1. Okay, so rate equals K. Again, I've got OI that's going to do the same thing, right? So I'm going to have H2O2, I negative. The OI is not going to be there, but H positive. And that's going to be third order, okay? Okay. So then let's take a look at mechanism 2 and see if it will fly. Okay. So the stoich we already found out matches. So let's see if the stoich will match on this one too. Change my highlighter a little bit. Okay. So let's see here. Hoi we know isn't going to be there. Hoi is going to cancel out. I2 is going to cancel out. And then we're going to look at the same thing again. So I'm going to have H2O2, one of those. 3 I negatives. Check, check. 2 H positives. Check, check. And over here, I'm going to have 2 waters and I3. Check, check. Okay. So far, so good. So notice how we've got to check to make sure the stoichiometry matches for each one. And then we got to find the rate law for each one. So we didn't do this one yet. Mechanism 2 with the first step rate determining. It's going to be rate equals K, H2O2, I negative, and H positive. I know I stole this from a multiple choice test thing you have on there, but we don't know the rate law, so it's going to depend on what the rate law is. Any of these could be correct, but on this one, by the way, it has to be the third order. If I were to ask you which one do I think it would be, I would expect it to be this guy because it's second order and the lowest order is most common. But it has to be, we need, I'll make this nice and big. To be given rate law. And we're not, so oops, I made a boo-boo. Write the reaction to the rate law for A through D above. We did that. All right. So I guess I changed my question there, didn't I? All right. The rate determining step is the slowest step. Imagine a reaction occurring moles of time. So remember, moles of times would be 10 to the 23rd times. Jillions and jillions and jillions and jillions of times. The steps have to wait for the slowest step. The slowest step is labeled. And people don't believe me when I say it's labeled. It's labeled. See how this says slow? Oh, slow. That's it. So I'll tell you the sad story. When I was in 5th grade basketball was a big deal in Indiana. Whoever came in last running sprints had to wear the slow jersey. So you had to wear the slow jersey to school the next day, and it said slow. It was literally labeled slow. So you worked your butt off to never be the last person, so you'd never be the person who wore the slow jersey. How do you know who the slow person was? They wore a jersey that literally said slow. So that's what these do too, slow. So what that would mean is, how do I figure out which one's the rate law? Rate equals K, slow. CL plus O, not plus, CL times O2. Oh, yeah, it's O2. Good. Okay. Maybe it's O3. I copied this to put it in a better writable thing, but I didn't get as good a stuff. Okay. Imagine reaction occurred moles of times the steps of slow step. The slow step is labeled. And there you go. So which one is it? Mechanism 1 or mechanism 2? So on this one, if we were to write the rate law for this, we would have to say that this is our slowest step. So rate equals K x squared. Now notice there is another reactant here. Y2 is a reactant. It's just not in the rate law. So that means I can increase it, but it doesn't make it go any faster. Okay? It doesn't make it go any faster at all. All right. Collision theory 5.5. This is a review. Okay, so we did this way in the beginning, but it comes back. For a reaction to be successful, particles must collide with enough energy, and collide with the correct orientation. Successful reactions are rare. Imagine throwing a baseball mitt and a ball in the air and having it be caught and stick. Throw them in the air, throw it at it. You got to have it hit in the pocket, have it close. Woof. 1 out of 10 million is not uncommon. That's how rare they are. Reactions involve bond breaking and bond forming. Barf. Break absorbs, release forms. And then we have Boltzmann diagrams again. Welcome back to Boltzmann diagrams. There'll be a line like this right here. This is my EA. This is my activation energy. So that's the energy it needs to have the reaction take place. If I'm over here, this is a big nothing burger. What happens here? Nothing happens. Here means it could happen. Okay? Shaded area is the only part with enough energy for the reaction to occur. Catalyst moves the line to the left. So if I'm a catalyst, I now make it go over here. And notice how that's a lot more particles that can now react. Okay? Boltzmann diagram shows essentially temperature. Hotter diagrams are lower and righter. Colder diagrams are higher peaked and lefter. So if I'm going to do a hotter one, hot of course is hot. Oh, I'll make it thicker. Hot. So it would be lower and righter. So it would be, and notice how they would have more particles under the curve. And that was almost it. So now our reaction energy profile. So these are potential energy diagrams. This is PE, so it's energy, and this is typically labeled time or reaction coordinate, okay? So what has to happen here is this is my first intermediate, okay? Reactants are the starting materials. They're found on the left. Reactants, okay? The products are the ending materials. They are on the right. Whoops, I'm not going to call those E, I'm going to call those P, of course. Here are my products, okay? May include catalysts. The transition states are the highest peaks, okay? So let's go green. We'll call that T sub S, okay? If you were to look at them, they're bad transition states because they're unstable. Remember, if you're unstable, that means you're going to fall apart, okay? So if I build an unstable clubhouse, what's the best, a tree house, what's the best way to tell it's unstable? It falls on the ground, right? So the transition states indicate the number of steps in a reaction. So this one is 2 steps. This one is 2 steps, right? Step 1, step 2. The highest transition state is the slowest step, okay? The slowest step is the rate determining step. Good. Activation energy is energy from the reactants to the highest state, not the transition state. So here we go. So this would be my activation energy. This is EA. I should change color. I'll change the color. Why? Because I am color gifted. EA. Okay? EA. Okay. Delta H is the energy of the reactant, energy of the reaction, bond energy. It's products minus reactants. So see how we have, go back to products minus reactants. So if this number is 50 and this number is 75, delta H is products minus reactants. 50 minus 75 equals negative 25 kilojoules. Okay? So ending low is exothermic, ending higher is endothermic. So this is exo, this is endo. Notice how this would have 1 step, 2 step, 3 steps. Okay? So again, those transition states tell you on the setup there. Okay? I do want to show you this. This one is a 1-step reaction. And this one is catalyzed. If you're, it's a Z, not an S. Catalyzed. And what that means is it lowers the activation energy. So notice 1 step, this has a high EA. This one has a lower EA. And remember, catalyzed means that it's faster. Okay? So a low EA, and EA, remember, is activation energy. Activation energy means faster. Now remember, being faster helps a ton when we're dealing with kinetics, but it has to affect the slowest step. So catalysts affect the slowest step. And I think I finally got everything in here. We're done with Big Idea 5. Woo, yay, Big Idea 5. And to that, I will say, toodles.